So we'll quickly do waves today, okay? So in your 11th part 2, you have some how many? Some 7 chapters, okay? Chapter 7 chapters. One is mechanical properties of solid. So all that I have taught is that Hooke's law, and then Young's modulus, rigidity modulus, bulk modulus, and all that. Okay, so that is a very simple one. Okay, so and then mechanical property of fluid. And so there I have taught you about say Pascal's law, Bernoulli's principle, surface tension, viscosity. So most of them are formula driven numericals. So, but we need to understand the region behind it. So I have explained you what is surface tension, what is viscosity, what are the main governing formulas in surface tension and viscosity and Bernoulli's equation of continuity. Using those 4 things, surface tension formula is viscosity, and then Bernoulli equation of continuity, you can solve a number of numericals. Okay, so it is important in physics to just not to remember formulas, but how it is being derived. But you cannot derive it in the exam, but if you know how it is derived, it is easy for you to remember. Okay, and do the numericals. Okay. Then thermal properties of matter, specific heat capacity, and then heat transfer, Newton's law of cooling. I think I had done it little early for you, heat transfer, Newton's law of cooling. We can go through the formulas one more time. I have already derived, we can go through the formulas. Okay, heat transfer, conduction, convection, radiation, Newton's law of cooling, calorimetry, that latent heat of evaporation, latent heat of melting, what is specific heat capacity, and all that. Okay. Then thermodynamics I had done long before. We can quickly do that quickly one more time. What is a heat engine? What is a refrigerator? What is the efficiency of a heat engine? What is the coefficient of performance of a refrigerator? How the efficiency and coefficient of performance differs? What is a adiabatic process? What is an isothermal process? What is a Carnot engine? How it is a cyclic process? It consists of 2 isothermal, 2 adiabatic process. What is the work done in a isothermal process? What is the work done in a adiabatic process? As compared to the kinematics, here if you develop the understanding, you can easily do the numericals. So it is statics, it is easy to do, but as compared to the kinematics, it may it may be little tricky and it may take little longer. But thermals, if you understand how the formulas are derived, the formulas are not complicated. Like say Carnot engine. If you know the concept, okay, the efficiency is equal to 1 minus T2 by T1. T2 is the sink temperature, T1 is source temperature. That's all, you can find the efficiency. Similarly, in case of a heat engine, your work done is the intended thing. So you are putting work done divided by heat input. Okay. So work done is equal to Q1 minus Q2. Q1 is the heat input, Q2 is the heat output. So work done by heat input. Input your fuel, whatever the calorific value of the fuel into mass of the fuel, that is your Q1. Okay, that is getting converted to mechanical work. So mechanical work done divided by heat input. So that is Q1 minus Q2 by Q1. So that is the efficiency of a heat engine. Similarly, in a refrigerator, what you are doing? Your Q2 is important here, because your sink, from your refrigerating chamber is your sink, and the room outside it is your source. So you are taking heat from a low temperature refrigerating chamber to a high temperature outside surrounding. So when you are doing that, you have to spend work. So as per nature's law, the heat will flow from high temperature to low temperature. But if you are trying to transfer heat from low temperature to high temperature, you have to spend some work. So Q2 you have to take from the refrigerating chamber, it will go to it will, with the help of some compressor work, it will be thrown out to the surrounding. So coefficient of performance here will be like say how much heat you are taking. Okay, so so it will be Q2. Q2 is your Q2 is how much you are taking and how much work you are spending for that. Yeah. So coefficient of performance will be Q2 by W. Okay. So Q2 W is again Q1 minus Q2. So it will become T2 by 1 minus T1 minus T2. So that's the difference between a refrigerator and a heat engine. Okay. And then different formulas for work done in isothermal process, adiabatic process. Isothermal process, the iso means same, thermo means same temperature. So from point 1 to point 2, so if there is an expansion or compression, that is called in any, when it goes from one point to another point, the temperature remains constant. So it is isothermal process is P1 V1 is equal to P2 V2. Whereas in adiabatic process, in isothermal process there can be heat exchange, but in adiabatic process there will not be any heat exchange. Okay. So the governing equation for adiabatic process is P1 V1 to the power gamma equal to P2 V2 to the power gamma. So that gamma is nothing but your Cp by Cv. Okay. So in general for diatomic like there is monoatomic gases, diatomic gases, triatomic. So in general for diatomic gases, Cp by Cv is equal to 1.4. So normally we will use 1.4 because your air consists of mostly nitrogen. Yeah. So nitrogen is diatomic. So that's why we are using. So for monoatomic, gamma will be different. So I have in kinetic theory I have studied that. In monoatomic, gamma will be different. Diatomic and triatomic gamma will be different, but we will be using diatomic one. Okay. So so now those are the things we will go through quickly. Then first law, second law, and third law of thermodynamics. Okay. So first law said heat input is equal to work done plus change in internal energy. Del Q is equal to del U plus del W. Okay. So and second law says that you cannot convert the complete heat input to work. No. You have to throw away something to this thing. To the surrounding or the sink. So that is the second law of thermodynamics. Okay. And then there is zeroth law and third law and all that. So and then specific heat and specific heat capacity. Okay. So say specific heat, the amount of heat required to raise the temperature of unit mass by unit unit degree, unit temperature. So Cp, there can be two Cp, specific heat. At constant pressure, constant volume. So del Q by M del T, that is your specific heat. Yeah. Okay. And only del Q by del T is your specific heat capacity. Okay. So we had covered all those things. We will go through it one more time. Then oscillations I had covered. That simple harmonic motion, there can be good number of questions on that also. So I have derived all those things. I will take you quickly through those formulas so that it will be easier. But sound, this waves we are not covered, so I will take you through waves now. Okay. So okay, so there are it's a big chapter, but we will just concentrate on the formulas and how it is being derived. Okay. So okay, so we'll start with speed of a transverse wave on a stretched spring. Okay, so speed of a transverse wave in a stretched string. Okay. Suppose you have a string, okay? So we'll start it with a numerical, okay? So the question is a steel wire. Where is my spec? Okay. So a steel wire of 0.72 meter long, okay? So 72 meter long has a mass of let us say uh, 5 gram, okay? So the mass of the steel wire is 5 gram, okay? The mass of the steel wire is 5 gram and its length is its length is 0.72 meter. 0.72 meter. And if the wire is under tension of 60 Newton, so it is under a tension of 60 Newton. It's under a tension of 60 Newton. Okay. What is the speed of transverse wave on the wire? Okay. So let us say I have a string. Okay. So this string you stretch it. You stretch it. The tension is 60 Newton. It is like this. It is a tension. Okay, it is being stretched. Tension is equal to 60 Newton. Length is equal to 0.72 meter. Mass is equal to 5 gram. This is the mass of the string. Yeah. Okay. So the speed of the wave on the wire. So what is the speed of the wave? Here so the formula for this is the formula for speed is equal to t divided by nu square root. Okay, this you have to remember. So what is this? What is this nu? Okay, this nu is mass per unit length of the wire. Okay, so this nu is nothing but mass per unit length of the wire. This you have to remember. So just you have to remember the formula. The speed of the transverse wave in a stretched string under tension is
root of
t by nu. T is the tensile force and nu is nothing but mass per unit length. Okay, so the mass is 5 gram, then mass per unit length will become, I have to put it in kg. Okay, 10 to the power minus 3 kg divided by 0.72.
Yeah.
Right. So so this will become, this is in meter. Okay.
You have to convert.
So this nu you will get as 6.9 into 10 to the power minus 3. 6.9 into 10 to the power minus 3 kg per meter. Okay. So now everything is in SI unit now. Okay. This is in kg per meter. This is in Newton. So when you have consistent unit, you need not bother. Okay. So now I'll get this velocity in meter per second, right?
Yeah.
This velocity I'll get in meter per second. So this will be 60 divided by 6.9. So this 10 to the minus 3 means this will go to the top.
Yeah.
Okay. So this square root. So this will become 60,000 divided by 6.9 square root.
Yeah.
So, so this will be approximately, let us say,
1.
1 0 0 0 0. Okay. So this will be something like 10 to the 4 square root, which is 10 to the 2 meter per second. So that is the approximate value, but the actual value is 93 meter per second.
You can round it up to 7 and divide. 6.9, you can round up to 7 and then divide.
So this is the correct value is 93 meter per second. So that's, you just have to remember there can be numerical on this. So you don't need to bother at this point how it is being derived. Just it is velocity is equal to tension in the spring divided by mass per unit length. Okay. So the mass per unit length is important here, not mass per unit volume or the density. Okay. So this is a string. Here the volume is not that important. Mass per unit length is important. Okay. So this you have to remember this. Tension divided by mass per unit length square root. Okay.
Yeah.
Take a picture of this. Okay. Now this is a typical example of speed of transverse wave. Speed of transverse wave in a string. Okay. Now we'll study speed of sound in air or whatever. Okay. Speed of sound in air. So now we in air, when air is the medium, okay, what will be the speed of sound? Okay. So speed of so what we have studied was transverse wave, but this is longitudinal wave.
Yeah.
So what is difference between transverse and longitudinal? When the motion is along the direction of wave propagation, that is longitudinal. If the motion of the particle is perpendicular to the direction of wave propagation, that is transverse. Okay. So what we have discussed earlier was transverse wave. Now we are discussing about the longitudinal wave or the speed of sound. Okay, this is longitudinal wave. Okay. Okay. So that we have taught about string. Okay. So where that is T by nu. You just remember the velocity of sound in case of this gas and all. Okay. So the velocity of sound is uh, so we have studied in case of liquid or gas, we are studying now we are studying about bulk modulus, right? So let us say this is my gas or water or whatever. So I am applying some pressure. Okay, so I am applying some pressure. Okay, so let us say I am applying some pressure. Okay, so my this got compressed to something like this. Okay. Okay, so this got compressed to something like this. My initial volume is V. My final volume is V minus delta V. Okay. So my change. So because so my volumetric strain. Okay. Volumetric strain is equal to change in volume by original volume. Change in volume by original volume. So this is equal to del V by V. Okay. Original volume was V. It got I am applying some pressure and it got compressed to this. Then we had studied about Young's modulus and we have studied about rigidity modulus. We have studied about bulk modulus. Okay. This is my bulk modulus. So this Young's modulus was nothing but longitudinal stress by longitudinal strain. So longitudinal stress is equal to F by A divided by del L by L. Okay, so that was my Young's modulus. Okay, then this rigidity modulus was my shear stress divided by my shear strain, which is an angle. So this one, so this is again F by A. If I am applying the force as shear load. Okay, so one is like this. And other one is like, say I had a rectangle and I am applying a force and it is getting deformed by an angle theta. So this theta is nothing but let us say this is your del x, that is the change in length, and this is your L, right? So this is tan theta is equal to del x by L, which is otherwise same as theta, which is nothing but your shear strain. So always remember that shear strain is nothing but your angle. So your F by A divided by your theta. Okay. So this is your shear modulus. Okay. Similarly, you have a bulk modulus for volumetric thing. So that is you are applying a pressure, then it is minus delta V by V. So this is your bulk modulus. Okay. And then it is not there in your scope, but this shear modulus can be related to this Young's modulus. Young's modulus can be related to shear modulus. So G is equal to E divided by 1 into 2 plus nu. So this is a property, you are not deriving it. Okay. So why I am referring this speed of sound, to bring in the concept of in air or in water, you are related to you are interested in volumetric change and you are relating with the bulk modulus. So we will bring in pressure here. So here, so whatever stress here you are measuring, here it is equal to pressure. Okay. So your bulk modulus is equal to P divided by del V by V. Okay. And then the velocity of sound in water or air is equal to this velocity. Okay, so I'll write it like this. Velocity is equal to square root P by rho. That you have to remember. Velocity is equal to, sorry, not P by rho, bulk modulus by rho. Bulk modulus by rho, not P by rho, not pressure by rho, bulk modulus by rho. Okay, so your velocity is equal to bulk modulus by rho. So this is valid for your liquid and gas. Okay, but when you get into solid, this velocity will be your Young's modulus. Okay, so are you able to understand? This you have to remember. These are the things which are just a formula, you should not leave it because you will spend very little time here.
Yeah.
Only thing is you have to be very, very careful about the units.
Yeah.
The LHS unit, RHS unit, if you have any confusion with your formula, try to match the unit of LHS with RHS, it will be clear.
Yeah.
So the velocity is equal to bulk modulus by density in case of gas and liquid, and gas and liquid, and velocity, so it is liquid or gas, this is solid. So because in solid there is no meaning of bulk modulus.
Yeah.
So Y is your Young's modulus.
For solid.
Okay. So from here you know, like normally this Young's modulus will be more than the bulk modulus.
Yeah.
Okay. So this Young's modulus will be more than the bulk modulus. The unit will be same, it will be more. Okay, so bulk modulus. So that is the reason you will see that velocity of sound in solid is much more than the velocity of sound in liquid and gas. Okay, so Young's modulus of material. So, so speed of sound in some media. Okay, so what is the speed of sound in? So you have a table where it is mentioned what is the speed of sound in different media. Okay, so I'll write one liquid, one solid, and one this thing gas. Okay, so let us say so the velocity of sound, okay, which is the longitudinal thing, okay, the longitudinal wave. Okay, so we told that the velocity of sound in liquid and gas is equal to bulk modulus divided by density square root. Okay. So this bulk modulus, this Young's modulus, or rigidity modulus, everywhere the unit is Newton per mm square only, or MPa. Newton per meter square you can say, but Newton per mm square is, which is MPa, is considered. Okay, so they are all same unit. So so how you will get the consistent unit? Because if you divide this B by rho, or so it will become, what it will become? So Newton. Okay. So we are discussing about velocity of sound in air or in water, which is a longitudinal wave. Okay. So we came to a conclusion that okay, velocity of sound in liquid and gas will be bulk modulus by density, and in case of solid it will be Young's modulus by density, and we are telling that bulk modulus unit is Newton per meter square, which is more conveniently called as Newton per mm square or MPa. So bulk modulus, Young's modulus, rigidity modulus, everything has similar unit. Okay, so and then we were about to write the value of velocity of sound in different medium. We told that because Young's modulus is higher than bulk modulus, so this is very obvious, because as you know the liquid, so it's a very tricky important thing. Liquid and some solids generally have higher speed of sound than gases. Okay, so so why does it happen? Because so it is very much more difficult to deform solid as compared to deforming liquid and gas. Okay, so here like say this is my this is my say Young's modulus. Say Young's modulus is nothing but stress by strain.
Yeah.
So for creating some amount of strain, the deformation, you need lot of stress.
Yeah.
Okay, whereas in case of liquid and gas, you need comparatively
Yes.
lesser pressure. Okay, you need comparatively lesser pressure. That's why this Young's modulus. So that's why you can say the velocity of sound in liquid and gas is less than that of solid. Okay,
Yeah.
and this modulus, Young's modulus, is higher than bulk modulus or whatever. So that is the catch. So we will take some typical value of velocity of sound in different material medium. Okay. So this is, let us say, in the left side I have medium. Okay, and then in the right side I have sound, speed of sound. Okay, speed of sound. So just remember, speed of sound is this. Then prior to this we had done for a transverse wave. Now we are doing longitudinal wave. Transverse wave, the velocity of sound was kind of T by nu. Okay, so T is the tension by mass per unit length. Okay, tension by mass per unit length. So you can always check left and right side to check whether your formula is okay or not. Okay. So let me write the velocity of transverse wave. Transverse wave is equal to T by nu.
Yeah.
So this is
Mass per
mass of string per
unit
unit
length.
length. So that is transverse. Now we are doing. So then let us say I'll write gas at, so air at 0 degree, air at 20 degree, air at 0 degree and air at 20 degree. Okay. So this is air, okay, one value air, then water, okay, water, then let us say steel, okay, steel, okay. So what will be the velocity of sound? In air at 0 degree it is 331 meter per second. Okay.
Yeah.
331 meter per second. If it is 20 degree, it will be 343 meter per second. Okay. So I will tell you what is the reason when temperature increases, density decreases. So because density is decreasing, velocity will increase. So you can take this tip like velocity is inversely proportional to square root of density.
Yeah.
Okay. So at a higher temperature, your density will come down.
Yeah.
Okay. And similarly, there are examples of yeah. So hydrogen and helium. There is so helium is 965, whereas hydrogen is 1284. Why they are more? Because air has nitrogen. So nitrogen is much more denser than helium or hydrogen. Okay. Helium, there can be question. Okay, helium is more denser than hydrogen because hydrogen
atomic mass is
so in hydrogen the speed is will be the highest, then helium, then air. Okay. So V hydrogen greater than V helium greater than V air. Okay. And then at higher temperature density will reduce, that's why velocity will increase. That is the things. Then liquid, it is 1402 meter per second. Okay. So this bulk modulus is nothing but your pressure divided by del V by del V. Because pressure by volumetric change. Bulk modulus is pressure by volumetric strain. So see, this strain is this theta is shear strain. Okay, shear strain. Okay, for solid we are considering longitudinal strain. Longitudinal strain for solid. Okay, and this is volumetric strain. That is for gas.
Yes.
Or gas or liquid. So we are considering volumetric strain. So this B is nothing but your P by del V by del V. P divided by del V by del V. So B. So then velocity of sound. So if we find the bulk modulus, then only we can find the velocity. Okay. So clear?
Yeah, understood.
Okay. So then water. Then steel. What is the value? Steel is 5941. Okay. 5941 meter per second. Again, here there can be tricky question. Aluminium, copper, steel. So aluminium and copper, again they are less denser than steel. So in aluminium the velocity will be more because the density is less. Okay. So aluminium it is 6420. Aluminium 6420 meter per second. So these are some of the interpretations you should be able to interpret. So only thing that drives those things is velocity is
inversely proportional to density.
so this is what is driving all those things. So this is driving density. There can be a number of questions which can be asked. Same air, high temperature and low temperature. So density is the key point. Okay. So you know steel is much more. So steel has specific gravity of say 8 or so. Aluminium has specific gravity 3. Right? By specific gravity means by how many times it is heavier. Okay.
Yeah.
So steel has more density. So if water density is 1000 kg per meter cube, steel density 8 means it will be 8000 kg per meter cube. I am just giving some representative value. Okay. So because so that's why you can see aluminum here you can see is the highest velocity of sound. Okay.
Yeah.
So when we say this subsonic aircraft, supersonic aircraft, there we compare that speed of the aircraft with the velocity of sound in air. Okay. When we say velocity, means normally we say velocity of sound means velocity of sound in air. Okay. So you when you see lightning, okay, what is happening? So after you see the lightning light, somebody will say, okay, there will be thunder now. Okay. Because the velocity of light is 3 lakh kilometer per second, right?
Yeah.
So light travels much faster. So you can see the light much faster. Whereas sound travels at a lesser speed than that of light.
Yeah.
So after some time you will hear the thunder, right? So that's so velocity of sound. So it is 332 meter per second. Okay.
Yeah.
So this 332 meter per second. So 332 meter per second, if you convert it into so if you convert it into kilometer per hour, you just have to multiply it by 18 by 5. Okay, 18 by 5. So it will become something around 11. So 1100 kilometer per hour. Okay.
Yeah.
So that is the velocity of sound. So the supersonic aircraft like MiG aircraft, its Mach number is 2 times. Mach number is speed of the aircraft divided by velocity of sound. That is called Mach number. So when Mach 2 means it is traveling at something around 2200 km per hour. Okay. But at a higher altitude, the density of air is less. So there the velocity, the Mach number may be, the velocity of sound may be little less. But not too much different. Okay. So at low altitude or at high altitude, there can be little bit of difference in density. Accordingly, the velocity of sound can vary. Okay. So at high altitude, when we are traveling at 11 kilometer, say 30 kilometer altitude, when we are traveling, the outside temperature will be minus 25. Okay. So as we go to the top, the density will decrease because we have less air. Yeah. Okay, but the temperature is less. So the temperature is less means they may give rise to increase in density.
Understood.
So those things we need to take into consideration. Okay, take a picture of this. Okay, so now we have the summary is velocity is equal to bulk modulus divided by density, right? So this bulk modulus is nothing but in gas, okay, in liquid or gas, this bulk modulus is nothing but pressure divided by del V. Okay, so now we'll go to the generalized equation like if you knowing the pressure, how to find the velocity of sound and all. Okay. So normally it is assumed that when this sound is traveling, this process is a isothermal process. So if it is a isothermal process, normally PV is equal to nRT. Okay, nRT. This is my equation. Okay.
Yeah.
So this n is my number of moles.
Moles.
Okay. So what is my number of moles? Number of moles is equal to my
In gas, how much? At STP.
So if n is number, n is equal to number of moles, n is equal to number of molecules. Okay. Okay. So yeah. So my number of moles is equal to number of molecules. Number of molecules divided by Avogadro number. What is that? 6.023 into 10 to the power 23. Okay. This is my number of moles. So this I can write it as n divided by r, n capital N divided by r divided by Avogadro number. Okay. Avogadro number. Okay. Into t.
Yeah.
Okay. So this is n. This is called K and this is called T.
Yeah.
So this K is nothing but your Stephen Boltzmann constant. You know that?
Yeah.
Okay. Boltzmann constant. It has a constant value. Okay. Like R has a constant value, this also has a constant value. Okay. So this is Boltzmann constant. So PV you can write it as NKT. N. So your K is R divided by Avogadro number 6.023 into 10 to the power 23. So this is NKT. Okay. So if this is the case, you can write this PV is equal to F. Okay. So this is a constant. Okay. So this is a constant. So this equation n is the number of molecules, K is Boltzmann constant, T is the absolute temperature of gas. So for an isothermal change, it follows from okay. So this equation, if this equation can be, if there is a change in pressure when sound is traveling, there is a change in pressure and change in volume. So this equation can be written. Okay. So we are discussing about velocity of sound. Okay. So this PB is equal to nRT, which you can otherwise write as PB is equal to N. N is the number of molecules. So this is in terms of number of moles. So if you want to write it in terms of Boltzmann constant, it will be number of molecule into Boltzmann constant into this. Okay. So this, when the velocity, the molecule is traveling in air, so it is normally there will be variation of pressure and volume. So this equation can be written as P delta V plus B delta P. Then because this is a constant, so its derivation will be 0. Okay. So this will be 0. So if this is 0, this equation can otherwise be written as, pressure can be written as, okay. So the pressure can be written as del P minus del P del V by V. Okay. So this term, this pressure becomes equal to bulk modulus. Because earlier I have told you, like say this is my circle and this is the one, and it is being subjected to pressure. Okay. So it is subjected to pressure. Okay. So this is volume V and this is V minus delta V. So your bulk modulus is equal to pressure divided by delta V by V. Okay. So here this pressure now, this bulk modulus is this term. Okay. So now you can prove in a isothermal process this bulk modulus is nothing but your pressure. Okay. So earlier we have told that my velocity in liquid or gas, or let us say in this case air, velocity in air is equal to bulk modulus divided by density. Now bulk modulus become equal to pressure, so it will become pressure by density. That is the main thing. Okay, so in a isothermal process, it will be your square root of pressure by density. So this you have to remember. Okay, the velocity of sound in air is equal to pressure by square root of pressure by density. So in your book there is a numerical. Yeah, you can take a picture of this. So there is a numerical. So now we have derived that okay, velocity in air is equal to pressure by density square root. Okay. So there is a numerical like estimate the speed of sound in air at standard temperature and pressure. So STP. Okay. There are these called standard temperature and pressure. The mass of 1 mole of air is 29 into 10 to the power minus 3 kg. Okay. So 29 into 10 to the power minus 3 kg. Okay. So you know standard temperature and pressure what it is, STP. Okay. So for to find the velocity of sound, you need to know density of air. Okay. So your density of air is equal to your mass of air divided by volume.
22.4.
Volume of air at STP. Volume of air at STP. Okay. So so you know volume of air at STP is 22.4 liter. Okay. So 20.4 liter is nothing but 22.4 into 10 to the power minus 3 meter cube, right?
Yeah.
And that is the volume. Okay. Then mass of air, that is being given as this much. Okay, 29 into 10 to the power minus 3 kg. Why it is 29? Because your 78% of your air is nitrogen. So nitrogen atomic mass is 20, molecular mass is 28, right? If this is N2, so 14 plus 14, that is 28. Okay, so 28. So this is so 1 mole of nitrogen will measure 28 gram, right? So that is mass of 1 mole of air. Similarly, volume of 1 mole of air. So this is nothing but 1 mole of air. Volume of 1 mole of air. Volume of 1 mole of air. Okay. So you are finding the density by considering the mass of 1 mole of air, then density of 1 mole of air. So mass of 1 mole of air and density volume of 1 mole of air. So this density you will find as 1 point. So density is equal to 1.29 kg into 10 to the power 3, right? So 10 to the power minus 3. Sorry, 1.29 kg per meter cube, right? Water density is 1000, whereas this is nearly 1. Okay. So density of air is 1.29 kg per meter cube, and then knowing the density and the pressure. Okay, what is the pressure at sea level? So your pressure is equal to like 1.01 into 10 to the power 5 Newton per meter square. That is one atmospheric pressure. So one atmospheric pressure is equal to 1.05 into 10 to the power 5 Newton per meter square. So I have explained you how it is being derived. So 1 ATA is equal to 760 mm of Hg. Okay, of Hg. Okay, so this is nothing but your rho into G into H. Okay, so knowing this, the G value, which is 980 mm per second square, and then height is 760 mm, and density that value. So knowing all these, you will find out what is your atmospheric pressure. So you know your atmospheric pressure, which is equal to this much. Okay. So just remember this one, 1.03 into 10 12. This is your atmospheric pressure at sea level. Okay. STP is nothing but pressure at sea level, pressure and density at sea level. So now after replacing all these things, if we replace like 1.003 into 10 to the 5 divided by 1.29 or whatever, if we do, we will end up with a value called 280 meter per second. Okay. So why this difference? Because the assumption that this is a isothermal process, when a particle travels through air, it's a isothermal process. There is dissipation of heat and the temperature remains constant. That assumption is not correct. So it is being explained that it is a adiabatic process instead. So
multiply by Cp by Cv.
So you have to multiply gamma here, and it will become gamma P by rho. So this 280 into gamma is nothing but your 1.4, right? So
for diatomic.
For diatomic. So normally it is diatomic. So 280 into 1.4. If that is the case, so this will become something like say 332 meter per second. So that is the accurate value. So where from this gamma comes, gamma is equal to your Cp by Cv. Okay. So your so gamma is normally for diatomic, it is 7 by 5. Okay, which is nothing but your Cp by Cv. Okay. So Cp is equal to 7 by 2r and Cv is equal to 5 by 2r. Right. So this becomes 7 by 5. So Cv you can derive first, which is 5 by 2r for diatomic. Okay.
Yeah.
Then Cp is equal to Cv plus r. Okay. So 7 by 2, so 5 by 7. So the velocity of sound is not gamma p by rho square root, but it is gamma p by rho. Okay. So that's the velocity of sound. So these are the things you should always remember. Take a picture of it. We'll go to the next. Okay, so there is something called reflection of wave. Okay, so just you remember, when the wave get reflected, there will be a difference of phase angle by pi. Okay, so okay. So normally the traveling, the wave that is traveling, it will be represented as y as a function of displacement and time, y as a function of x and time is equal to your a sine kx minus omega t. Okay, so this can go in detail. So it is a function of position and time. Okay, so this is the equation of wave motion. So if the reflected wave equation will be, you have to add pi to it. So y reflected will be equal to a sine kx minus omega t plus pi. Okay, So if this is the case,
this
sine
is
1.
there in wave optics also.
Okay. So this is there will be a difference of pi. Okay. And then we'll get into normal mode and all that. Okay?
Nodes.
Yeah. So there are different types of pipe, like say open pipe, closed pipe, and all. So there, what will be the velocity? Okay, the fundamental frequency. Okay, fundamental frequency. Yeah. If a string is fixed at both ends, okay, so its fundamental frequency, yeah. So there is a numerical, if you do that, we will understand. So a pipe of 30 centimeter long is open at both ends, okay. So I have a pipe, it is open at both ends, okay, and its length is 30 centimeter, okay, its length is 30 centimeter, okay, it is open at both ends. What is the harmonic mode of pipe? What is the harmonic mode of pipe resonant at 1.1 kilohertz? Okay, so in this case, so let there be air inside this pipe, and the velocity is the sound is moving through this. Okay, so when it is moving, so normally in case of a open pipe, so in case of a open pipe, and the harmonics will be like this. Okay. It will be something like this. So it will be something like this. So the first harmonic frequency is nothing but V by 2L in this case. So the first harmonic, the frequency, first harmonic. So this nu is, you can write as nu. Okay. If there is a confusion, you can write as frequency. So first harmonic frequency is equal to V by 2L. Okay. So this is air here. So your air. So you just remember this V is nothing but meter per second, and length is again meter. So this is like say per second. So from here you can correlate. Okay. So frequency is equal to V by 2L for a open pipe. Okay. First harmonic is equal to V by 2L. Okay. And if it is if the pipe is closed at one end, let us say if my pipe is this and it is closed at one end, if the here pipe is opened at both ends, if it is closed at one end, my fast will be V by 4L. This also you should remember. Fast harmonic. Okay. Velocity by 4L. If it is closed at one end. Okay. Similarly, S. Okay. So the first 6 harmonics of vibration of a straight string fixed at both ends. So if you have a string, okay, so the string is fixed at both ends. So you have a string which is fixed at both ends. So the first harmonic will look like this. Okay. So it will look like this. So this is the first harmonic. Okay. This is the first harmonic, and the second harmonic will be same. It will vibrate like. So this is my second harmonic. So it will. So this will become my second harmonic. Okay. So so here also the formula for this string also it will be same V by 12, and this is my length. Okay.
Yeah.
So the length between the two support is L, then first harmonic will be V by 2L. But here you have to the string in that case you have to find out the okay, the fundamental frequency. So okay, for a stressed string fixed at either end, it is given by V at V by 2L, okay, corresponding to N by N is equal to 1. Then the for other harmonics will be, the generalized formula will be N by N into V by 2L. Okay. And if suppose here it is fixed at one end, okay. So if your pipe is fixed at one end, your first harmonic will be V by
4L.
so V by 4L. Okay. So now your question is a pipe of length 30 centimeter, sound is traveling through this at 330 meter per second.
330 by 6.
So your V by 2L is equal to like say 330, then this 30 centimeter you can convert to meter. So it will become
into 2. Into 2. 2L.
Into 2. So if this is the case, your frequency you will end up with 550. Okay. 550 hertz. Okay. 550 hertz. So they are asking where the resonance will happen. So your 1.1 kilohertz they have given. Okay. Kilohertz. Okay. So 550 into 2, you know, it is 1100. Okay. So this is nothing but 1.1 into 10 to the power 3, right? So this is 1100, right?
Yeah.
So into 2. So the second harmonic will be will cause the resonance. You might have done your experiments, right?
It's there in wave optics.
Yeah.
Similar.
It is similar. Then you can.
After that, Doppler effect is there in wave optics.
Okay, so Doppler effect also is.
It's like superposition. It's there.
So when you have source of sound and you are moving away.
Yeah.
So when you are moving away, what will happen to the frequency?
Apparent sound
yeah,
and.
So that is Doppler effect when you are approaching and when you are moving away. So the new frequency, that formula is equal to V is equal to V0 into
Vs
1 divided by V by Vs.
Vs.
Okay.
Yes.
So this is when source is moving away, your velocity will, your frequency will decrease. Okay. So if it is moving away, it will be minus. Okay. If it is coming closer, your frequency will be plus. Right.
Yeah.
So your S is frequency of your source. Okay. So this is your let us say Doppler change in frequency of wave detected when source is moving towards the observer. So let us say this is my observer, this is source. So some sound is coming.
Yeah.
When it is coming closer, your frequency will increase. So this is the formula. Okay. When it is going away, frequency will decrease. So you have a numerical related to that. So a rocket is moving at a speed of 220 meter per second towards a stationary target. Okay. So let us say, yeah. So this is my target. Okay, and a rocket is moving.
No,
okay?
target is stationary. Object is rocket.
Okay. Okay. So this is my object. So this is my
Target.
This is rocket, and this is
Target.
Okay. So this rocket is moving at 200.
220.
No. It is moving at 200 meter per second. Okay, it is moving at 200 meter per second towards a stationary target. Okay. While moving, it emits a wave of 1000 hertz. So its rocket is the frequency is V is equal to 1000 hertz. Okay. It is emitting a wave of sound. Okay. Then find the frequency of sound are detected by target. Okay. When it is moving, what will be the frequency of sound? Okay. So it will be so it will be 1000 into like 1
plus because it's going towards
1 plus like say velocity. You have to compare it with the velocity of sound, right?
Velocity of sound is 1.
So sorry, actually it is the velocity of sound will be at the numerator. Okay, I made a mistake. This is velocity of sound. This is v.
That is V naught, no? That denominator. No, okay.
No, v naught is this. Okay, this is velocity of sound.
Yeah.
Okay, so your velocity of sound is this one, which is 332 meter per second.
Yeah.
Okay, then your velocity of rocket. So you don't confuse, these two are frequency.
Yeah.
This is the
Velocity.
sound. So this new is confusing actually. So,
Write it.
so let me write it as capital V. Okay, so this is velocity, right?
Yeah.
This is velocity. Okay. Velocity. So whereas this is frequency. So what will be the new frequency? What they are asking, the frequency of sound as detected by target. So this is my rocket and this is my target. So it is emitting a sound of frequency 1000. But what the target will see? The target will see it as like say 1000 into 1 plus velocity of sound that will be in the numerator 332. 332 by 200. So this will be something around 330. Okay, so I think so this is, so the main thing is the velocity will increase. Okay, the frequency when it is moving towards it, the frequency of the wave, the frequency at which it senses will increase. So the frequency when it is approaching towards it will increase by how much? By an amount Vs by V. So Vs is the numerator, that is the velocity of the sound. V is the at which the object is moving. Okay. So that is about Doppler effect. So you can go through all these. Okay. So now I have covered harmonics, Doppler effect, velocity of sound. So you can go through all the formulas and practice as many as possible. Okay. Thanks.